Hello everyone and welcome to Texas Tech University's Project Lab 1 tutorial videos. I am one of the tutors for this course. My name is Daniel, and in this video I'm going to be showing you how to create a PWM signal from a module on the BASYS3 board. So to get started, we're going to talk about what a PWM signal is. You should have talked about it in Digital System. Not you can go to Google and search PWM. There's various different resources that explain PWM and several tutorials on how to create PWM. But basically, PWM is a technique. It's called pulse width modulation, and it's a technique to create these different width pulses to get different outcomes on a digital system. So as we know, our BASYS2 board outputs a logical 0 or a logical 1 through its outports, so PMOD ports or any other general I/O port. So that 0 on the BASYS2 board, this logical 0 is 0 volts, and for the BASYS2 board, the logical 1 would be a 3.3 volts. So I know this image shows a 5 volt for the logical 1, but this is just an image for the Arduino here. So in the BASYS2 board, we do have a logical 1 represented as 3.3 volts. Do not want to take any 5 volts, anything higher than 3.3 volts. You will damage the BASYS2 board and the input pin. Alright, so pulse width modulation again is just a technique to create these pulses, and these pulses get created by a sequential 1, so a bunch of 1s and a bunch of 0s. They get repeated in a set period, so different components run at different periods. Period can also be thought of as the refresh rate on whichever component you're working with. So if you're working with a servo that has a refresh rate of like 60 hertz, your period would want to be of 60 hertz, so that way you are giving it the signal it needs at the time it's looking for it. Alright, so again, in this set period, here we can see that in this set period it is constantly off, so it is 0% on, so the duty cycle, we would call this having a 0% duty cycle. Here we see that the signal in this one period is on for 25% of the time, so therefore we would say it has a 25% duty cycle. This one 50 and 75, and then this final one you would see that it's 100% of the time on, so therefore it has 100% duty cycle. So what this does to a component that you're working with, so say if you're working with a motor, this PWM, this pulse width modulation technique, allows us to control the speed of the motor. So in this 0% duty cycle, we have 0 power going to the motor, so therefore it wouldn't be moving. In this 25% duty cycle, it would be moving about 25% of the speed, because we have 25% of the power going to the given motor. And in this one, 50% of the speed and 75% of speed and full 100% speed on the motor. So when you start working on your module to control the H bridge to drive your tank or your rover, you will see that the H bridge has 2 pins, an enable A and enable B, that can take a PWM signal and allows you to control the speed for that motor. So the H bridge is broken up to the A side and the B side, and enable A allows you to control the speed on A side, and enable B allows you to control the speed on the B side using this PWM technique. Alright, so another application that PWM is used for is to turn on or brighten up an LED or a light. So here you see that with a very thin, narrow pulse, the light is almost off. Here with a half pulse on, you see that it's a little bit brighter. And here with an almost full pulse, you see that it's the brightest. The LGB or the RGB LEDs, the red, green, blue LEDs, also use PWM to change the different colors. So it has a red and a green and a blue leg that if you change the PWM on each one of the legs, the LED turns on a different color. Another application for PWM is for the servo. Creating pulse widths of certain size will move the servo to a given position. So this is just an example of, I'm sure it's not a real servo, the specs, the period, and the pulse width for each servo should be given in a data sheet. So if you grab a servo from the stock room, go to the data sheet and it'll tell you what the period should be and what the pulse should be for that given position, and then it should tell you for center position and for furthest right position. So to operate a servo with PWM, you can get with me later and I can show you that. But in this module we are just going to create the basic PWM and simulate it. Okay, so to start making our module for PWM here, I'm going to open up Vivado, create a new project. I'm going to label it PWM underscore tutorial. Hit next. RTL project, family Yardic 7, package CBG 236, speed grade -1, and then XC7 835. Finish. Alright, so this will create an empty project for you that we can write the Verilog module to create PWM. So first we want to come over here to our sources and add a source. We're going to add create design source, so hit next. We're going to create a file. We want a Verilog type. I'm going to call it PWM underscore tutorial. Okay. Finish. And for now, I'm just going to hit OK. Yes. And that'll create this blank module called PWM tutorial. I'm going to double click it so we can open it up and look at the module. So if we look at the module, we see that it's a standard template for an empty module. So you just have the timescale, your header, and this all the module currently includes. So I wrote a PWM module a little bit ago. So here's the code I wrote. I'm going to copy it. So I'm going to copy it and paste it in our module. So made sure that I paste it below the tutorial module name. So now we can go back and talk through this module, and you could copy this module as I talk through it. So going through this module, we see that we have 3 inputs and 1 output. one of the input here, this first one is clock, and it is set to a default 1 bit. Here this other input is called speed, and here it is set for a 2-bit input, so it's a 2-bit array, and we can think about it as having position 1 and position 0. So the 1:0 says that we have position 1 on the left and position 0 on the right, and those are the only two positions we have. This reset says that we have an input called reset, and again it's default to 1 bit. And then we have an output called PWM, and it's set to a default 1 bit. Alright, so that explains all of our inputs and outputs. Here we see that there's no comma on the last entry, which is standard for Verilog modules. So moving on down, we see that we have 3 registers. So what this module is actually doing, if we look at our PWM signal here, the first register, the register called counter, sets the period, as it says here in the comment. So this counter sets the period. So we see that this counter is a 5-bit array. So if we think about it, this counter can only go from 0 up to 32 or 31. If you wanted to calculate how much a 2-bit number can store, what the maximum number of a 2-bit number, it would be 2 to the power of 5. So 5 bits can go from 0 to 31. So you do have to count the 0 because it has 32 positions, and 0 is position number 1. So with that in mind, we know that the counter can count from 0 up to 31. And since the counter only has 5 positions, once the counter is full, so once the counter has the value of 31, we know that if we add 1, it resets all the bits back to a 0. The result would be a 1 followed by 5 zeros, but since we only have a 5-bit number, we only evaluate these 5 bits, and that 1 disappears. So with that in mind, we can think about it as starting from this green line at 0 and counting up to 31, and once you increment again, it goes back to 0 and starts back up to 31, and that's how we repeat that cycle and repeat this pulse. Alright, so that's the first counter. Like we said, it just sets the period. If you wanted a longer period, you would grab your calculator again, and we know that the BASYS board has a oscillator of 100 megs, so 100 megs, 1, 2, 3, 1, 2, 3. And say we wanted to create a 60 hertz clock, so 100 megs, we know it counts up to 100 million in 1 second, and we're going to create 60 times in 1 second. So if we divide that by 60, it tells you how much you have to count up to create 1 tick of that 60. So using the 100 meg oscillator, if you count up to what is it, 1,666,000. If you count up to that, that would be your first tick, and you count up to that again, that would be second tick, count up to that again, third, fourth, fifth, and that's how you create 60 hertz. So whatever period you're trying to create, like I said, you just grab the oscillator that you know is on the board, which is 100 megs, and you divide it by the period you're trying to create. So create a 60 hertz, and you know you need a counter of that big to count up to create 60 hertz. So this period only goes up to 32. This is a real fast period. I created this really small period just to show you when we create a simulation that it is doing what it's supposed to. but for most standard applications you want to have a period of around 60 hertz or greater. Alright, so that's what this first register does, is just a counter that increments from 0 all the way to 31 to create that pulse. And this next register is a width. So that register will store the value of the desired width. So on this 25% duty cycle, if we wanted a 25% width, we would divide our number 32 divided by 4, and we know that the answer is 8, so all you have to do is for 8 ticks output a 1, and then for the remainder of 32 ticks you would output a 0. So for the first 8 ticks you would output a 1, and then the rest of it you output zeros, and you create this 25% duty cycle. For the 50% duty cycle, we know that to create the whole period is 32. So if we put 16, from 0 to 16 to output a 1, and from 16 to 31 to output a 0, we will create this 50% duty cycle. Alright, so register just stores the width of the desired pulse. This register, temp PWM, as we see, our output is PWM, and since Verilog does not let us manipulate the output directly, so if we replaced all these temp PWMs by PWM by itself, the output PWM, Verilog would give you errors saying that you cannot manipulate an output, so therefore we usually create registers that we can manipulate, and then at the bottom we assign the registers to their appropriate output. So again, here's the register we can manipulate, and we assign it to the output that it corresponds to. Alright, so that explains all three of those registers. Here the next block that you would come into is initial begin. This is a way to initialize values in all of these registers. So it is good to put an initial value in one of your registers, so that if we come to this line and we don't have a value, Verilog won't know what counter plus 1 would be, because we never put an initial value in counter. So therefore it is good to initialize all of your registers with an initial value, so that once you start doing operations to that register, they are logical, and Verilog does understand what value should go in there. So another thing, initial begin, this only happens once, so it'll, very first time, it'll initialize all these registers with 0, and then it will never do it again, and it won't affect your code. So the next thing we see is this always at positive edge of clock block here. What this says, this always at argument here, says that anytime the argument is true, we would do everything inside this begin and end statement. So this always at block says that anytime it identifies positive edges of clock. So as we know, the clock goes from 0 to 1, 0 to 1, 0 to 1, and oscillates back and forth. So that rising edge from 0 up to 1 is what this positive edge of clock identifies. So every time it identifies a rising edge of the clock, it will do these two if and else statements. Looking at these if and else statement, this first one, you see that if reset is true, if reset is pressed, then we will zero the counter back to 0. Else, if reset's not pressed, then we can increment the counter. So here, this first part, all we are doing is incrementing the counter every time we identify the oscillating clock. So as the clock changes from 0 to 1, we increment the counter. Alright, so this next if and else statement. This next if and else statement creates the pulse. So as you see, if the counter is less than the set desired width, Let's go back here. So say that the width is 8. So if the counter is at position 0 through 8, we want to output a 1, a logical 1 to create that high part of the pulse. So when the counter is less than the set threshold, it'll output a 1. After the counter goes greater than the set width, then it'll output a 0, creating the trough of the pulse. So this if and else statement actually creates the pulse that we output as our PWM. Alright, and then looking at this last always at block, again, what's inside of the parentheses is the argument, and in this case star means anytime anything changes. So anytime anything in the code changes, we will do everything that's inside this begin and end statement. And in here we are just updating what width should be based on speed. So as we know, speed is our input, our 2-bit input, and based on what that input is, we have a set width. So if the input is 0, the width is 0. If the input is 1, the width is 8 to create the 25% duty cycle. If the input is 2, the width is 16 to create the 50% duty cycle, and 3 would be 24 to create the 75% duty cycle. Alright, so the last thing we would look at would be this assign statement. Again, it's just assigning the output to the manipulated register called temp PWM. So that explains all of this block code here that I wrote. We can go ahead and save, and then we can synthesize the design. Alright, so once you have saved your module, go ahead and run a synthesis. So I have already completed my synthesis. Again, all you have to do is save your module, run your synthesis. That'll take a few minutes. Synthesis will check for syntax, and then you should get this window. You don't really want to run implementation. You would run implementation once you have set up your constraints to assign all your inputs and outputs to their location on the board. But what we want to do now is write up our test bench to demonstrate that this module works. So to create a test bench, I'm going to create add source here. Go to add create simulation source, hit next, and we're going to create a file. It's going to be Verilog type. I'm going to call it PWM underscore tutorial underscore test bench. So that's just a standard naming convention that this is the test bench that goes with that module. Hit OK and finish. And again, we'll just hit OK for now. Yes. And we want to go here to our sources, and under simulation you should see the PWM tutorial test bench module. So you want to highlight it, select it, make it blue, and then under source file properties you want to scroll down and you want to make sure that only the simulation option is selected. So unselect synthesis. This is a test bench. We only want it to exist in simulation. So only the simulation one is checked off. The other two are unchecked. And now we can double click on that test bench to open up the module. Alright, so looking at this module, we see that it is just looks like our empty blank new module. So to write this test bench, you have a couple simple steps. Step 1 is to go back to your tutorial module or to your module that you're making a test bench for, to copy all of your inputs and outputs. So I'll copy those and I'll paste them inside my test bench. So here you want to make sure you paste them outside of that parentheses, semicolon, or parentheses and semicolon here. So just out here, I will paste all these. And step 1 is to change all of your inputs to registers. So all of our inputs will be registers, and all of our outputs will be wires. So, as in standard coding convention, you have to end each one of these lines with a semicolon. So this is different than labeling your inputs and outputs. Your inputs and outputs would go inside the parentheses, but in this module we don't have any inputs and outputs, we have registers and wires. So once you have copied and pasted all of your inputs and outputs and made them registers and wires, then the next thing you want to do is instantiate the module that you want to test bench. So instantiation to instantiate. So you just want to write the name of the module, pwm_tutorial. It has to be exactly the way it's spelled, so pwm_tutorial, and give it a local name, which here I'm giving it UUT, stands for unit under test. And then you can open and close parentheses, and inside your parentheses you're going to add all your inputs, so clock, speed, reset, followed by your outputs, PWM. So this is one way to instantiate. This is the easiest way to create your test benches, just because you got to remember all you need is your name of the module you want to instantiate, local name, and then open parentheses and add your inputs and outputs. So to check to make sure that instantiation went through correctly, you can save it, and once you save it you can look in your sources here, and a correct instantiation should place the module that you are test benching underneath the new module that we called test bench. So as you see, this is a test bench. This is the test bench you're writing, and PWM tutorial is listed underneath it. So it has correctly instantiated it, and we are ready to add some stimulus. So to write some stimulus, you just need an initial. Make sure you spell it correctly. Initial, begin, and the first thing you want to do is zero all your registers. So clock will be 0, speed will be 0, and reset will be 0. So I'm going to add a little bit of delay, so 10 ticks. And now we can start changing our stimulus to evaluate the different options. So clock, we're not going to be changing it. We just wanted to set an initial value, but speed and reset we can definitely change to see what the different inputs have cause the output to do. So in here we can change speed. We'll do it 1, add some more delay, so we'll add like 300. Here we can change the speed to now 2, add some more delay. And so a good test bench, you want to evaluate all the different possible inputs you can have just to see what the module does in all the cases. So we know that our speed can go from 0 to 3. It's a 2-bit input, so it can go from 0 to 3. and add some more delay. And then the last thing we want to do is check the reset. So we do a quick press of the reset, short delay, and then zero everything back out. Alright, so this creates all of our stimulus. Again, we are just manipulating the inputs that go into this module called PWM tutorial. We are manipulating the inputs to see what the output's gonna do. So that is how we check all of our inputs. Again, that's all inside the initial begin. That it creates all of our stimulus, and now to create an oscillating clock, you just want to do an always begin, and you can do #1 clock equals not clock. So this will so this is an inverter, so it'll just invert the clock every 1 tick. So every 1 tick it'll do this and invert the clock and create that oscillation that would happen on the BASYS board. So the 3 steps that you need to create a test bench is inputs and outputs to reg and wires, instantiation, and then your stimulus. Only other thing you want to keep in mind is anytime you are using a clock, you have to simulate the clock to oscillate too. So our test bench is finished. We can go ahead and save it and resize it back down, and now we can run simulation. Run behavioral simulation. And this will pop up the simulation window, which you can see the status of each individual bit and how the output reacts to the modified inputs that we did. So squishing it over here a little bit, press this and zoom to fit here, and we can see that let's see, so here are our outputs. Try to show you the names here. So this is clock, speed, reset, and PWM output. So as you see, when it was 0, the PWM was 0. Then we set the speed to 1, which will create a 25% duty cycle. So here you see that's about 25%, 25%, 25%, 25%. And then speed gets set to 2, which creates a 50% duty cycle. So again, that's about 50%, 50%, 50%, 50%. And then 3, which is about 75%. So 75%, 75%, 75%, and so forth, so on. Here, pressing this one allows it to run for that much time. So we let it run a little bit more. We see that reset gets pressed, and it zeroes out our PWM and zeroes out our clock for a minute. And you see that since speed is 0, the output PWM is 0. So now this simulation should show you that the module we created is creating the appropriate PWM signals based on the speed input, and it is also resetting when necessary. So this test bench shows that our module works as designed, and the next step would be to implement design and to generate a bit stream. But again, and just for time, I am not going to uh, generate a bit stream and program the BASYS3 board, you can do that on your own. The only other thing I would like to mention is had to adjust this for speed. So here our speed is only 2 bits, which those 2 bits can only go from position 0, or they can only represent the value 0 to 3. So therefore we only have 4 different duty cycles. If you wanted more duty cycles, you would increase that this input to 3 bits. 3 bits would give you 9 positions, so you would have 9 different speeds. 4 bits, 16 speeds, and so forth, so on. When you do that, you got to make sure you spread out the widths so that you create more different duty cycles. Again, 4 just gets divided in 25. 9 you would have, I don't know, like 10% increments or 9% increments, and so forth, so on. So yeah, if you wanted to use this PWM tutorial module for anything else, like I said, you would probably have to set the period to whatever you were working with, and you would want to change the speeds so that you have as many different options as you need. That's it. This is a good PWM module that can be modified to whatever you need it, and in future videos I hope to show you how to instantiate this module inside of another module so that you can control this module using something like a top module and still get different PWMs. If you didn't know, you can also instantiate this module as many times as you want in a different module. So if you had to create different PWM duty cycles, you would instantiate this multiple times and then just input the desired PWM that you want on each individual one. Alright, so yeah, like I said, I will show you that in future videos, and I hope you learned something, and let me know if you have any questions.